Okay, so we basically talked about the behavior cloning algorithm, right? So it's literally a supervised learning algorithm. And now let's just put it into this Markov decision process framework. And again, we're going to focus on this discounted infinite horizon setting. And here, wait, what I'm doing. So here, the reward function is still a scalar from 0, 1, but this is unknown now. Okay, so your learning algorithm is not to be able to access it. Like you don't know the analytical form of the reward function, and you don't even see the reward signal. Right? And now let's assume that we have an expert that is almost the optimal policy. All right, so this is just for simplicity, for our analysis simplicity. We don't have to assume the expert policy is the optimal one. It could be a near optimal one, right? It's kind of hard to believe, human actually can output a policy that it is actually the optimal policy for this Markov decision process, right? But we could reasonably believe that the human expert is actually deploying a policy that nearly optimizes the underlying reward function, the reward function that in his or her head, right? It's just, we don't know how to write it down in math. All right, so we have a data set here, which is in the form of state action pair, where the state is sampled from the expert policy. Sorry about that. This should be initial distribution mu. So the state is sampled from the expert state distribution, and the action is sampled from the expert policy. All right, so this is our data set. The goal is to learn a policy from this data set, and the goal is to make sure that the learned policy is probably as good as the expert policy, pi star. Right? So here, if your expert is a terrible policy, then you can't do that much, right? In terms of, the best you can hope is, as good as the expert, right? Because that's the only learning signal you have at this moment. Right? So the reason that we call it offline is that the data set is the only thing that you have access to. All right? You're not allowed to test your policy on the robot to collect further data. So this is called offline imitation learning in the sense that the only thing you have is the data set. All right? I collect the data set for you on this robot. I ask you to learn a policy, and then I will take the robot away. You're not allowed to collect further data on the robot. This is called offline setting.
Can I ask a question?
Yeah.
What is an example of online imitation learning here? It seems like imitation learning is always going to be offline because you are mimicking an expert, right?
Yeah. No, it could be online. It could be online. So the approach, the method that they used for this Boston Dynamics little dot is actually an online approach. All right. So we will talk about that. So the idea is that you learn some policy, you can test it, see how it goes, right? And then maybe you can collect further data, and then you can refine your policy.
So when you collect more data, then you have expert to actually correct those data.
So yeah, so this is one particular setting, right? So imagine you have an expert that you can query during training time. Like, you literally say like, oh, I failed at this time. Like, let's call my expert and ask what she would do if she were in this situation, right?
I see. All right. Got it. Thank you.
Okay, let's not worry about this. Let's worry about that, in the next lecture, right? Next lecture, we'll talk about this setting. Okay, but this is a very reasonable setting, right? This is, for safety reason, I'm not allowing you to test your policy on the real system, right? I just collected good data for you, and you do your best to learn a policy, okay? Testing your policy on the real system is risky, right? Like, you might make a mistake and you might destroy the robot, right? The ideal case is that, if we can do reinforcement learning or imitation learning purely in offline, that would be amazing, right? Because from the safety perspective, this is kind of the most safest way to do things. Right, so the BCA algorithm is literally just a classification algorithm, right? So let's just consider a restricted policy class pi, right? Where inside this class pi, we have a policy. Like literally think about this policy as a classifier, right? That takes the state as input and classify it to a particular action. So the number of action is the number of classes you have here. Right? So BC is a reduction to supervised learning in the sense that once I have this data set, state action pair from the expert, right? I can actually apply a classification algorithm if my expert action is discrete, right? So using some loss function. Right? And I'm just going to search for a policy that minimizes this loss function averaged over the entire training data set. Right? So this is nothing fancy here. It's literally, multi-class classification problem. Right? So examples for the loss function, the first thing you can do is this negative log likelihood. Right? So for multi-class classification, we use maximum likelihood estimation. Right? So here, this loss function is saying that, under your policy, what's the likelihood of your policy generating the expert action at this state S star, right? So we want to make sure that, you find a policy which has high likelihood of generating an action that is similar to the expert, right? So that's the maximum likelihood estimation means, right? For those policy who generate action that are widely different from the expert, these are not good policy, right? From this classification learning perspective, right? So here again, your pi could be whatever policy you're interested in, right? It could be a decision tree, it could be SVM, it could be a deep neural nets, right? It's just a classifier. And if your actions are continuous, then we can formulate this as a regression problem, right? So we can just rewrite this loss function using square loss. So this is saying that what's the difference, what's the norm of the difference between the action you predicted and the expert action, right? And let's make sure that we find a policy such that the average deviation from the expert action is small. So that's what this least square is trying to do, right? So these are these two loss functions are probably the most common loss function that you would use for classification and regression respectively. Right? But the bottom line here is that, we reduce this to a supervised learning problem, right? So use your favorite supervised learning algorithm here. Okay, so let's just quickly analyze this. All right, so we're going to use this reduction approach again. Okay, so here the assumption is that we are going to assume supervised learning succeed. Okay, so if you recall, the quick brief intro that we had on supervised learning a while back, right? So what we said is that we can guarantee supervised learning succeed if the test distribution is the same as the training distribution. Right? If there's no distribution mismatch, then supervised learning, they should work. They work in both theory and they reasonably working well in practice as well, right? If there's no distribution shift. So in other words, here literally we can assume the following thing is true, right? Under my training distribution, so this is my training distribution. Remember, we collected data from the expert demonstration, right? Right? So under the training distribution, the classification arrow, in the sense that the action that I picked by my learned policy does not match to the expert action, right? The classification arrow is less than small number epsilon. So again, epsilon here could roughly equal to be 1 over m, where m is the total number expert samples. Right? Let's not worry about the details of epsilon, but what we assume here is that supervised learning succeeds in the sense that under the same distribution, the distribution where we collected training data, the classification arrow is small, is reasonably small. Right? And this classification arrow should go to 0 if you have more and more training examples. So that's all we assume. Right? So this is reasonable. So nothing is fancy here. We're just training our function pi hat from this distribution, and we are testing the prediction error under the same distribution, right? So the most common supervised learning setting. Okay, our goal is to see actually can we transfer this epsilon to the performance of the learner policy, right? Because this is the performance of the policy is literally what we care, right? So we care V of hat pi, right? Specifically, the performance difference between our learner policy and the expert policy. Okay, so any questions so far before we talk about, before we apply the performance difference lemma to get to quantify the difference between the learner policy and the expert policy? So that's pretty much the algorithm, right? It's simple. It gives you flexibility to use the classifiers here you want, right? So if you today are aiming for a policy that has some sort of interpretability, then maybe use your favorite decision tree algorithm, right? And if today you only care about the performance and you just want a black box policy that drives the car well, use your favorite deep neural nets, right? So you have a lot of flexibility and freedom to choose different classifiers or regression or regressors here, right? At the end of the day, we just map this to a supervised learning problem. And then now the last step we want to do is let's transfer this supervised learning error back to the performance that we care about, right? The policy's performance. All right, so what are we going to show is that, ignoring this high probability statement, this algorithm will actually return a policy pi hat whose performance is comparable to the expert policy pi star, right? Up to this gap, which is epsilon times this quadratic blow up in the time horizon, 1 over 1 minus gamma. Right? So in high level, this is actually pretty cool, right? My algorithm never uses the reward signal, but it's able to actually match the expert up to some gap in terms of the unknown reward function, right? Assuming that the expert is doing reasonably well under this reward function, then my learner policy is actually doing reasonably well under the function as well, under the unknown reward function as well. All right, so to prove that, at this stage, you probably can guess what's the first step we're going to use, right? We care about the performance difference. So then, of course, let's start with performance difference lemma. Right? I'm just writing out the performance difference lemma. So here, for simplicity, I'm just using deterministic policy. Okay, so here, both pi star and pi hat are deterministic. Right? Imagine pi star is a deterministic policy. Imagine expert is deterministic, and your learner is, the SVM, right? Which outputs something that is deterministic as well. But we can generalize this to stochastic policy very easily, right? So this is a performance difference lemma, right? I care about the performance between the optimal policy, the expert, and my learner policy. So I can just write this in performance difference lemma in the sense that now I'm care about the advantage against my policy averaged over the expert state distribution, right? So this is the advantage of the expert against my policy. And I'm averaging over the first policy, which is the expert policy. Right? So this is PDL. All right, let's just subtract a term, right? So this, what does this term say? This is the advantage of myself. This is the advantage of my policy against myself, which by definition is 0, right? Because A pi SA is Q pi SA minus V pi S, right? Remember, we talked about, right? So this advantage, like the advantage of your policy against yourself is 0, right? There's literally no advantage, right? So I just minus a term that is always equal to 0. Okay, so now we are in good shape, right? So we have expectation in both terms, both of the expectation are the same, and we have a function advantage and advantage on both terms, right? The only difference is that the action are different. Right? Let's just upper bound this. So what does this mean? So if you look at this expression, right? This expression is equals to 0 if pi hat s equals to pi star s. So that we agree, right? So if my policy outputs the same action as the expert, this expression is just equal to 0, right? But this term, this expression will be at most 2 over 1 minus gamma if pi hat s is not equals to pi star s. And the reason is that the advantage function is always in the negative region, 1 over minus gamma, and positive 1 over 1 minus gamma. Right? I'm just bounding this expression using the worst possible case. Right? If pi star s is not equal to pi hat s. Right? Because in this case, the first term in this expression is at most 1 over 1 minus gamma. And then the second term is at least negative 1 over 1 minus gamma, right? So the difference will be at most 2 over 1 minus gamma. So that's why we arrive at this expression, right? So this is an indicator function. So if our policy disagrees with the expert, this is the maximum thing that we're going to pay, right? 2 over 1 minus gamma. Okay, so this is nice because under this expectation, the indicator under this expectation is literally the classification error. Right? Let's just replace this classification error by our supervised learning error, which is epsilon here. So we get this bound. And now you're rearranging terms. Remember, there's a 1 minus gamma here. Right? So that's the end of the proof. It's literally like 3 lines of proof. Right? So we successfully translate the supervised learning error back to the performance of the policy, right? And critically via this PDL. Okay, so before we talk about the issue of this algorithm, any questions about this algorithm and its very simple proof?
Professor, where does the factor gamma come from? Because like here we're reducing reinforcement learning to like supervised learning. So you have training data, you have action, but you like during the whole algorithm, you never have to actually introduce the gamma term here, right?
Correct, yeah. But remember what we did here is translate the supervised learning error performance back to the reinforcement learning problem, right?
Yeah.
So this V is still the expected total reward, right? So this V is still expectation of like sum over H gamma to the power of H R S H A H. Right. So we are just using performance difference lemma here.
Okay.
Right. Remember what this algorithm gives you is a policy pi hat, right? But what you care is the performance of this pi hat when you execute it in the Markov decision process.
Okay.
Right. So you still care about the performance of the policy inside this Markov decision process, right?
Yeah. Okay. So basically you're saying the gamma factor here, that is, so you have to choose that when you're designing the value function, and then you pick that gamma, and then gamma is the 2 over 1 minus gamma factor.
No. So the gamma factor is given when the MDP is defined, right? So remember, we interested in solving this MDP problem.
Yeah.
Which is SA, gamma, P, and R, and the initial distribution, right? So we are still interested in finding the optimal policy for this Markov decision process, right? It's just that at this time, this reward is unknown,
Okay.
but we have as a pair sampled from a near optimal policy.
Okay, I see. All right, thank you.
Right. So that's the information you have. Right. I mean, your goal is still to find a policy that maximizes the underlying reward function, right? So in other words, we reduce this reinforcement learning problem to supervised learning, and then we translate it back to the reinforcement learning. So that's a route that we take. Right. So here, yeah, go ahead.
So didn't the performance difference lemma have a expectation over all the actions as well?
Yeah. So that's why I said, for simplicity, let's just focus on deterministic policy. Let's assume in both pi star and pi hat are deterministic.
Right. Okay.
Right. You can do the same thing for stochastic. Just replace, just start using expectation over actions.
Mm-hmm. Okay.
Right. So it's not super difficult to generalize.
So sorry, what was the purpose of the term, adding the term of the advantage of the learn policy over itself? What was the point of that in the proof?
Yeah, so I want to compare, because I want to introduce, so I want to compare my policy to the expert policy, right? So introducing this term allows me to compare these two, right? It allows me to compare these two actions, right? So if the actions agree with each other, then this is fine. If they're not agree with each other, we're in trouble. But what we know from supervised learning is that the chance that they disagree with each other is tiny. Right, so that's the logic behind why we're introducing this term. Okay, great. So now let's talk about the issues. Right, so if you record the video that I showed you, where in this driving video game problem, where the expert can actually drive for a long time, but what you saw is that the learned policy from this behavior cloning algorithm can actually just drive the car for a while, and then eventually it falls off the track. Right? It can do well, reasonably well, but it's not really as good as the expert. Right? So the real issue is this quadratic blow up, so which is actually pretty annoying. Right? So we pay supervised learning epsilon, but when we translate it back to the performance, we pay this quadratic blow up. And why this isn't any issue, right? So this is related to the question that some of you asked at the very beginning of the lecture. All right, so let's talk about the distribution shift issue in behavior cloning. So this is literally the issue. All right, so this figure is literally demonstrating the issue. So you have the expert demonstrations represented by this very nice, dashed blue trajectory, right? But when you learn a policy from the expert demonstrations, and when you drive the car using your learned policy, we're probably going to make a mistake, right? Because supervised learning is good, but it's not 100% accurate, right? You're going to make some mistakes gradually. And maybe you start making mistakes somewhere here. And you're going to make more mistakes. And the more mistakes you made, the more far away you're from the expert demonstrations, right? So when you get to these regions, like from the learner's perspective, from the algorithm perspective, or the policy perspective, it doesn't know what to do because it never seen the expert demonstrations in this region, right? Like here, we do not have feedback from expert. Right? Like once we deviate, we don't know how to recover because expert never tells us what to do if he or she were there in that situation. Right? So this is the problem. Like this is a real problem here. And that's why you saw in these video games, the learner policy actually can only drive well for a while and then, start to deviate and then gradually fall off the track. Because once you deviate, you have no idea how to recover because the expert never showed you how to recover. Because the expert can always drive very, very well, right? So intuitively, this isn't an issue, right? We can actually, quantify this issue using a concrete example. Right? Any questions about, this distribution shift issue? Right, good. So this actually demonstrates, why, reinforcement learning or imitation learning is different from supervised learning, right? Because there's a distribution shift problem. Like in supervised learning, we learn a classifier, we test the classifier on the same, this data distribution. But in reinforcement learning, you learn some model, you learn a policy, you have to drive the car using your policy, right? In other words, you're consistently testing your policy under the data generated by your policy, not the expert policy anymore, right? Not the data generated under the expert policy anymore, right? So you have to make sure that learn the model is doing well under the new state that is being generated from your policy, right? So that's the real, challenging here. Okay, so let's.
Can I ask a question?
Yes.
So when we are learning the policy, right? So let's go back to the car example. So you have an image of a car, and then the steering angle, right?
Correct. Yeah.
So you're collecting a lot of this, so snapshot of images and the steering angle.
Yes.
But aren't they not IID here?
They're not. Yeah, they're not. So yeah. So
Then
this is another. Yeah. So
use supervised learning to learn on this. Isn't this a problem?
Yeah, you're right. So this issue is related to the issue in policy gradient, right? So we talked about how to get, if you really want to IID samples, how to get the IID samples, right? So you just collect a trajectory, randomly pick a time step, keep that state action pair in that time step, and throw away the rest state action pairs, right? And draw and ask the expert to provide another demonstration, and repeat, and so on and so forth, right? So if you truly want to maintain IID, you're gonna throw away the data.
I see.
Right, so that's the loading process that we talked about, right? So you randomly pick a time step, you ask the expert to execute the policy, and you stop there, and you throw away the rest of the data, and you repeat this loading process many times. Then you guarantee that every state action pair you have in the data set is IID, right? But in practice, do you really want to do that? Do you really want to sacrifice the amount of data you have just for the purpose of getting exactly IID training data? It's probably not, right? Yeah, so there's a trade-off, right?
I see. Got it. Thank you.
I mean, one thing you can do is you just collect the all state action pair, randomly shuffle them, right? To make them, as random as possible. Now, of course, this does not really guarantee everything's IID, but from the learning algorithm perspective, maybe from the gradient descent algorithm perspective, the samples that it's seeing is sort of independent across different time steps, because at least you shuffle them randomly, right?
But if the data is not IID, then the learning bounds that we have for supervised learning, those won't apply anymore, right?
This won't apply. Yeah. I mean, unfortunately, in theory, we do need IID assumption, right?
Right. So in the previous slide, when we were analyzing that epsilon over that quadratic term, it could be even greater than that, right? Because the data is not.
It could be. Yeah. But that's this is really the choice of, this is really theory and practice disagree with each other, right? And hopefully you have tried the homework problem, at least the programming problem. So there, what we were doing is averaging all the state action pair that we have on these trajectories, right? So what I suggested you to do in the homework is that instead of doing loading in many times, throw away many samples, let's just keep all the state action pair and averaging them to get a policy gradient. Now, again, this formulation of policy gradient is not going to be unbiased, right? Because your samples are correlated, but they should work pretty well in practice because you're leveraging all the samples, right? So you're sacrificing the IID-ness, but you're using more samples. So there's always this trade-off you want to play around in practice. Okay, so let's talk about this particular example. And we will see why this quadratic blow up is actually not avoidable, right? So this is not, some artificial, sort of amplification we introduced in the proof. This is actually real, right? So in the sense that you cannot actually, in theory, improve the quadratic blow up. You have to suffer. Right? So let's look at this very simple Markov decision process. And S0 is the initial state. And I have two actions, A1 and A2. And everything is deterministic. Right? Now let me tell you the expert policy. So expert picks A1 at S0 and picks A2 at S1 and picks A1 at S2. So in other words, if you start from the initial state, the expert will just go here and then self-loop forever. Right? So the expert policy, expert trajectory is very simple. It just move from S0 to S1 and then stay at S1 forever. Right? So in fact, the expert will never visit S2 because it doesn't need to. Right? Everything is deterministic. Okay, so you can actually calculate the state visitation from the expert policy. So here I did the homework for you. So you can actually show that the expected state visitation, this expected state distribution at the initial state is 1 minus gamma. And then the rest of the probability will be concentrated at S1. And then the expert has 0 probability of visiting S2. That matches to this trajectory, right? So what we said is that the expert started at S1 just for one step, right? And then immediately it moves to S1 and they're going to stay at S1 forever. So you have tiny probability of visiting S0 because you just started at S0 and then you immediately move to S1, right? But you have a lot of probability of staying at S1 because once you get to S1, you're going to do self-looping there. You're going to stay there forever, right? And you have 0 probability of visiting S2 because the expert policy never goes there. Okay, so now let's assign the reward function. So let's see, the expert policy is actually doing some work, right? So here the reward function is 1 at S1 and 0 everywhere. Right, so I have rewarded 0 everywhere except the S1. So the expert policy is doing a very good job. It immediately moves itself to S1 and then do self-looping at S1 so that you can collect reward every time later on. Right, so the expert policy is actually the optimal policy for this Markov decision process. Right, I calculate the expert total reward, expected total reward for you. So in this case, the expert total reward will be gamma over 1 minus gamma. Right, so the reason is that experts get rewarded 0 at the first time step because it starts at S0, right? But then immediately gets gamma times 1 plus gamma squared times 1, so on and so forth, right? Because once you get to S1, you're going to keep collecting rewards. Right? You're going to get 1, 1, 1, 1 all the time, all the way to the to the end. So you just discount them properly, and this gives you gamma over 1 minus gamma. Right, so this is the optimal policy. Like if I give you this MDP, right, the optimal policy is actually the expert policy, right? Because if you were at S2, the optimal policy, the optimal action to take at S2 is actually take A1, right? Because you want to immediately translate to the rewarding state so that you can start collecting rewards. So the expert policy is literally the optimal policy here. Okay, so now let's see, I run this behavior cloning algorithm and I learn a policy pi hat. Okay, so this is some policy pi hat that I made up for you. So this looks a little bit complicated, but let's see what this policy is doing. So if you look at state S0, so this policy says that I will pick A1, I will follow expert A1 with reasonably big probability. So think about epsilon as a small number, right? So it's a tiny number, right? So it says that with probability 1 minus epsilon over this 1 over 1 minus gamma, I will follow the expert, right? Most of the time, I'm just listening to expert. I'm just going to follow A1. And with this small probability, this is small, I'm actually making a mistake, right? So with some small probability, I will deviate from the expert, but most of the time, I'm fine. I'm just following the expert, right? So this means that at S0, I have a little probability of making a mistake. This is my classification error, right? Okay, at S1, my learner policy happened to be the exact optimal policy, right? Because at S1, my policy is also picking A2, which means that I'm going to get a lot of rewards once I get to S2. Sorry, S1. Right? So now let's look at S2. So at S2, my learner policy is actually not matching to the expert policy, the optimal policy at all. So my policy is actually picking this action. Right? So I'm doing a terrible job at S2. So I'm doing a reasonably good job at S0. I'm doing perfect job at S1, but I'm doing a terrible job at S2. So that's all this example is saying. Right? But from supervised learning perspective, like this policy pi hat is a pretty damn good policy. So in other words, we have really good supervised learning error in the sense that the expected mistake that you would make under your training distribution will actually be bounded by epsilon. Right? So the reason is that if you recall this distribution, right? So let's just calculate the expected mistake that I would have made at every state, right? So at S0, I have 1 minus gamma probability of visiting S0, right? Because this is from here, right? But under S0, what is my mistake, right? So my mistake is epsilon 1 over 1 minus gamma. Right? So this is the pi star S0, S0. Right? What about at S1? So I have gamma probability of visiting S1. And I have 0 probability of making a mistake. I never make a mistake at S1. Right? My policy is perfect at S1. Right? And now I'm actually making a lot of mistake at S2. But this is okay because the expert in the training data, the expert never visited any S2, right? Because this is 0 times 1, where 0 is the pi star, S0, S2. Again, the expert never visited S2. So even our supervised learning algorithm make a mistake there, it doesn't know that it's a mistake because you never see any feedback at S2. Right? So from the supervised learning perspective, this is pretty good because your classification error is epsilon. Right? You're doing really well on the state action pair, on the state that showed up in the data set. But for those states outside of this data set, like you literally have no idea, right? Like you have no idea what expert would do at S2 because you've never seen that in the training data. So that's literally this expression is telling you, right? So you have 0 here. So this 0 is important, right? So this says that this state, it never shows up in the training data. So you making a mistake, yes, but that's fine from the supervised learning perspective because under this training data distribution, you're doing fine. Right? So in other words, your supervised learning algorithm literally can output this policy because this policy is really good from the test error perspective, right? Okay, but when you map this policy back to the reinforcement learning problem, right, we can calculate the policy's performance under this Markov decision process. And again, I did the homework for you. So here you will actually see that for this policy, the performance is actually this particular expression. And remember this V pi star is gamma over 1 minus gamma. So in other words, we have shown that there is a gap between our learner policy and the expert policy, right? And the gap is this particular term. and the gap actually is scaling quadratically with respect to this 1 over 1 minus gamma. Right? Because once your policy pi hat makes a mistake here, your policy is just going to stay here, right? It will never ever collect any reward. Like once you deviate from the expert trajectory, you're going to make a mistake forever. Right? So that's pretty bad. You don't know how to recover, right? The ideal case is that once you hit S2, you should maybe try A1. But we don't know that because expert never tells us what to do at S2. Right? So your supervised learning algorithm returns a policy. You just stuck at S2, unfortunately.
Sorry, how did you get that first part of the equation?
You mean this term?
Yeah.
Yeah, so you can calculate two cases, right? The first case is that the policy does not make a mistake at S0. So what's the reward you would get?
Gamma over 1 minus gamma?
Yeah, but you have to multiply it by the probability, right? So let's maybe calculate that.
Oh, right, okay.
Yeah, so basically, literally, you can so because the pi hat is well specified, you can actually calculate the value at S0, right?
I see. So you're just taking the expectation over the actions.
Yeah. Everything is deterministic except the first time step, right? So let's just calculate that. V pi hat S0. So this is, with probability, 1 minus epsilon over 1 minus gamma. I will take A1, right? But once I take A1, I will be good because my policy will actually self-loop at S1 too. Right? So this means my reward will be gamma over 1 minus gamma. Right? But what's the second event? The second event is actually I make a mistake at S2, at S0, right? But the probability of making a mistake is epsilon over 1 minus gamma. And once I get there, I get reward 0. Right? Because I will do self-looping at S2. And I have 0 reward for this event. I hope my calculation is correct. I think it's correct, yeah. So basically you discuss two cases, right? Like if I take A1, then I'm in good situation. If I take A2, then I'm in bad situation. Then you weight different two events, with their probability. Right? That's literally what we did.
That makes sense. Thank you.
Yeah, so this example basically demonstrates that, once we make a mistake at S0, unfortunately, no machine learning algorithm is perfect, right? So we ended up in S2, which is actually not in the training data. And unfortunately, we have to make a mistake. Unfortunately, we cannot avoid to not make a mistake there, right? Like we cannot guarantee that, your learned policy will not make a mistake at S2 because it never seen that. Like from the learning algorithm perspective, taking action A2 and taking action A1 at S2 are equally good because you've never seen these data, right? So maybe your algorithm just committed to S2, who knows, right? Maybe with 50% chance, it just committed it to A2, right? And sometimes in some day, maybe by chance, you committed it to A1, then it's good, right? But you can't guarantee that because you don't have control to that, right? And as we show in the video example, you do actually make a mistake. That could actually happen, right? Like your supervised learning algorithm just freak out, whenever it sees something that actually never showed in the training example, right? Like you lost control in those states. Okay, so what we covered so far is that this is actually a real problem, right? It's a real problem in the example that I showed you, and it's actually a real problem in this particular Markov decision process, right? This is a very simple Markov decision process, right? Like it's very simple, reward is simple, transition is deterministic, expert policy is simple, but nevertheless, we could still make a mistake. We could still suffer this quadratic blowout. Right? You can go ahead and create many, many more such kind of Markov decision process. Same issue going to happen. The fundamental issue is that, expert does not cover every possible state. So once you make a mistake, you don't know how to recover. Right? So again, back in 30 years ago, these researchers actually identified this problem for us. So in their paper, they said, if the network, which in this case is a policy, is not presented with sufficient variability in its training examples to cover the conditions it is likely to encounter, it will perform poorly. Right? I literally copied some sentences from that paper. So when they were doing these experiments, when they were doing behavior cloning these experiments 30 years ago, they identified this issue, right? So this means that, if we train the car in Pittsburgh and when we drive it in California, then we're going to be in trouble, right? Because we don't have demonstrations from California. Right. So in order to how to fix this problem, we will talk about it in the next lecture. Okay, so let's just do a quick summary for today. So we talk about the most common imitation learning algorithm, right? The algorithm people actually do use in practice. So this is a reduction to supervised learning. So the idea is that you collect examples from the expert demonstrations and you train your favorite classification algorithm on it, right? The classifier is the policy that you're going to use. And we talk about this distribution shift issue. So when we execute this learner policy, we may deviate from the expert trajectory, right? So this is bad. This is going to cause compounding error. The further away you're from the expert, like the higher possibility that you're going to make a mistake, right? Because the state that you currently encounter is actually widely different from the expert trajectory. So your learner policy is starting making weird mistakes, right? And then the mistake compounding over and over again, and you eventually going to fall off the track, right? You never know how to recover. And again, this demonstrates why reinforcement learning and imitation learning is harder than supervised learning, right? Because we need to test our model on the new data generated by our model itself, right? So this is not, a classification problem. This is not, a face recognition problem, right? The data is generated by your model, not, some fixed process that's never going to change forever, right? Okay, so that's all we want to cover today. And again, I will stay for